So very good to be here. As I thought about what I would talk about today, maybe in a more general sense, I want to talk about charged states in conducting polymers or in conjugated polymers. Well, we'll talk a little bit about conductivity, as Seth touched on. What we will not talk about really has to do with where we think conductivity can go. And I think as we saw the talk this morning from Chris, the fact that they were reporting a conductivity in a polythiophene of 5,000 Siemens per centimeter is quite impressive. And a team that we have here at Georgia Tech working on this feels that this is really just the beginning towards really making metallic conducting polymers. We'll be talking about that today, but it's a real important path forward. Based on the talks you saw both from Plextronics and from Boeing, I do want to talk on electrochromism and on charge storage in these systems. So I always like to start my talks with baseball to get things started a little bit here in terms of how people in this field interact. And for those of you that are baseball fans, what you know is that around the turn of the century, and that's the 19th to the 20th century, the double play was in essence optimized in baseball by this group, Tinkers, Evers, and Chance. And the idea is that they combined smooth fielding, accurate and rapid throwing, and secure catching with which to accomplish this creation of 2 outs, 2 out of 3 outs in a single inning. And you can see here the shortstop for the Atlanta Braves there that is completing a throw to first base in a very contorted way, doing his job. And the idea here for us is that as chemists, physicists, material scientists, and device scientists, we come together to work on these kinds of problems, and that really is one of the big benefits of COPE. I think a number of you know that we've moved my research group here over this last year, and really appreciate the opportunity to work with this group here at COPE. Let me just say, more senior people up here, and then we have some more of the newer people that are coming in with new results and new techniques in materials processing, materials characterization, and device processing. So another thing I really have to point out is, as Bernard talked about, the aspect of COPE and how it brings our students together is especially important. And I always want to acknowledge the students and the research groups that do all this work. So conducting polymers, conjugated polymers, you go back to basics, and a system that we've worked on for a number of years are based on dioxythiophene type systems. Specifically, these are propylene dioxythiophene systems that seem to have lost some methyl groups here, but we'll ignore that right now. The general idea being that the neutral polymer then can be created as a film. The film can be prepared by either electrochemical polymerization, if you're looking at small electrode-adhered materials, or by solution processing, and I'll talk quite a bit about that as I go along today. And then there's an electrochemical oxidation of that material or a chemical oxidation of that material in order to form a delocalized cation radical and then ultimately a dication, a so-called polaron or bipolaron, that give these high levels of conductivity. And what's especially important as we think about taking these materials to the next step, as polymeric materials, they're lightweight, solution processable, mechanically flexible. And as we think about how we can put them into various kinds of applications, we can think about the form factor of those applications, and I'll talk about that a bit when I talk about capacitors. Now, this brings together some important interactions and collaborations across our research groups here. Seth talked about this molybdenum oxidizing agent that was developed in his group. And then I have to talk especially about the development of this polymer here, which in the early days was called Spray-Dot Classic. In essence, a sprayable dioxythiophene polymer. And I would be reticent to not show the picture of the fellow who did this work. And so this is now Dr. Christophe Grenier, who's sitting right here, who developed this polymer. And this is a picture I've gotten a lot of mileage out of over the years as he's made this sample of this magenta-colored polymer. The point of the interaction with Seth's group is the ability to oxidize this polymer. And what you can see is that the pi to pi star transition is in essence fully bleached, showing that this oxidant is extremely good for this polymer. And then we have a near infrared absorbance that is growing in during the oxidation process. In essence, this is chemical chromism that you're looking at right here. Now, as Seth pointed out, they've been working on a number of dopant systems on the p-type side and on the n-type side. This shows the structure of that reducing agent that Seth was talking about, and work that's gone on in collaboration between his group and the Breda group in looking at how this molecule acts as a reducing agent, for example, reducing fullerenes. Now, as we think about carrying out these types of oxidations or reductions, in essence doping reactions, one thing to think about when you think about polymers is that we have a continuum of doping states. If we think about a salt, we might have a positive ion and a negative ion. But as we look at interactions, for example, in this F4TCNQ, as a function of various materials, you can see that there's a certain level of charge transfer as a function of how the dopant interacts with the polymer. And so there's a matching between the dopant and the organic system, both polymeric and in this case a molecular whole transporting material that controls the level of that charge transfer. Okay, so if we can control this level of charge transfer chemically, we can also do this electrochemically. And one way to think about using this then is to think about how we might use this to store charge. And so you can imagine we have a current collector with an electroactive polymer deposited on there. And we can set that electroactive polymer in its charged state or its dope state, and then have another electrode where we have that same polymer, for example, in its neutral state. And if we create an electrochemical device, we have a voltage or electrochemical potential between these two states. And now if we, in essence, short the system, if we allow the system to come to electrochemical equilibrium, then we are discharging our cell. And we can go back and forth between charging and discharging, and this is in essence how a battery would work, or more specifically for how these work as a supercapacitor type of a material. And so again, I'm going to be talking about how the form factor of polymer films on flexible electrodes can make this potentially useful. What you're looking at here is you're looking at a photograph of a laminated supercapacitor, in essence, that we've built using this dimethyl propylene dioxythiophene polymer. And a couple things that I want to point out here. First off is the overall capacitance of these systems. Electroactive polymers and composite materials can attain capacitances on the order of 200 to 500 farads per gram. And so there's a significant amount of capacitance that is obtained because they are conducting, they have very open morphologies. Ions penetrate rapidly in and out of the system. And so you end up with a relatively high level of capacitance. The other part that's important is the speed. And you can see here this material is being switched at 2 volts per second back and forth between the charged and the uncharged state. This is important when you compare the capacitor to that of a battery that's storing charge and is much slower. And then finally, the fact that we can charge and discharge these many, many times, and this is 30,000 deep discharge cycles on one of these polymer capacitors, flexible and flat. Now, since they're flexible and flat electrodes, we can bring these together and we can stack them. And you can see the word I've used for this in the past is that of a Dagwood sandwich. If you imagine bringing lots of layers together, in essence stacking multiple capacitors together with a bipolar electrode bringing these two together. And in essence what this allows us to do then is to combine these flat capacitors into modules. And so if you look at the capacitance here in black of a single device, you see that we have on the order of 8 millifarads per square centimeter with a cell that's operating out to almost 1 volt. Now, if we bring these cells together in these laminated devices in series, then we are in essence able to double the voltage that that cell can bring. And if we bring 4 of these together, we've shown how that you can go out to 4 volts in a single cell. On the other hand, if we connect them together in parallel, we're in essence adding the currents together, and we increase the overall capacitance of the system. And so we can build both the capacitance and the voltage in these laminated devices. Now, from there, what I want to do is I want to move over to the change in the optical properties of the materials as we carry out this charge and discharge. And over the years, we have developed what we call the full color palette of electrochromic polymers, polymers that give us all of the colors of the spectrum in essence, all the polymers that are needed for printing, for example, cyan, magenta, and yellow, all based on these very electron-rich structures. And you can see the pure dioxythiophene, you can see copolymers with relatively electron-neutral systems like phenylenes, and then donor-acceptor systems with things like benzothiazole here. And what's important about these polymers is that they are switching from a vibrant color state. This is a film that's been spray-coated onto an electrode sitting in a cuvette. You can see the counter electrode and the reference electrode sitting here. And they oxidize into a highly transmissive state. And so just like we showed with the oxidant, the moly oxidant, in the reactions with Seth's group, we bleach out, this is transmission data, we bleach out that color and we move into a highly transmissive state with most of the absorbance being in the near infrared. And this works for all of these colored materials. Now, let me just show you how we can apply this in a small device type. And what you're looking at here is you're looking at what would be an ITO glass with a coating of our polymer on there, and another ITO glass with the same on the back. If we put an electrolyte in the middle, and we, in essence, imbibe this electrolyte with titania, then we have a white reflecting inner layer. We can then set this, as we did with the capacitors, one neutral, one oxidized, and so the polymer in the front will be colored, the polymer in the back will then be in its transmissive form. When we change the bias then on that cell, that front polymer will then go into its transmissive state while the back polymer goes into its colored state. And you're looking at that here in this photograph of the ECP-Magenta going from its colored state here, and then here you're looking through that polymer at the titania. And you can see from the reflectance data on the order of 50 to 60% transmission through the entire visible range, a nice colored state in terms of 10% reflectance at this point. And in essence, what we have is we have a pixel that mimics that of an electrophoretic, but we have the ability to do this for all colors. As was mentioned this morning from the Boeing talk in terms of the possibility of changing colors on surfaces, in essence, you can mix these colors, you can create any colors you want, earth tone colors, etc. Let me just show you, in essence, how these work. These are some devices here on the left that we build in our lab. You can see that we are chemists. We're not engineers. We use silicone and clips and all that. But you can see if we switch these devices at, say, a second or a quarter of a second, that they switch quite effectively. Now, if you think about an e-reader, the switching time that you want is on the order of half a second, because that's, in essence, the amount of time it takes to turn a page in a book, and people are comfortable with that switching time. Another area then is signs and advertising, and we collaborate with BASF in this project, and they have collaborators, a company Invisible from Portugal, who then has put together these cards, in essence using the electronics that you get just as you would have from a card that plays music. But the idea was to create some kind of an advertising sign that would draw the eye. And so you can see here the ECP-Magenta now switching between its colored and its transmissive states. And if you're in a situation in a store where you wanted to be able to attract someone to your product, you could have something like this, a very inexpensive throwaway electrochromic device on a flexible substrate. Now, one of the things that we have to think about when we're doing academic research is what are the students observing? And where do those unexpected results come from? And it came for us, in the study of these dioxypyrrole polymers that are N-alkyl substituted. Now, dioxypyroles are the most electron-rich of all of the conducting polymers. They're the easiest to oxidize. But in essence, what we do is we break conjugation by putting a large group here, in essence, to force these pyrrole rings out of plane. Because it's so electron-rich, the electrochemistry of the polymer is still at a very low potential. It switches between its neutral form and its oxidized form very effectively. But what we were surprised to find was that we saw very little change in the color of the material upon oxidation. You're looking at the transmittance here, and you can see that the onset of the pi to pi star transition for the neutral polymer is here right around 400 nanometers, and so the film is very transmissive to your eye. But upon oxidation, you end up in the fully oxidized form having well over 80% transmission through the visible range, and most of the change in the absorption is in the near infrared. And so you have a very little color induced in the oxidized form of the polymer, and so we call this minimally color changing. In fact, if you use colorimetry and you look at the luminance, in essence what your eye detects as the transmissivity of the polymer, then you can see as a function of the film thickness, there is very little change in what your eye is sensing as the transmission through that polymer. So it's a material that's infrared active on the surface, but has very little change optically. What this is going to allow us to do is to put these then into windows where we want to switch our polymers that are vibrantly colored relative to this as a counter electrode, or have window systems that do not have color changes. And so with that, we've been moving over to higher levels, let's say, of processing in our lab. We've been using ultrasonic spray coating in our lab and are adding slot die coating as a processing method. Now, these are some photographs that come from a collaboration with Frederick Krebs's group in Denmark. And what you can see here is the slot die coating of the ECP-Magenta polymer onto flexible ITO PET, and then electrochromic devices that were built using this polymer as the color-changing polymer, using our MCCP as a non-color-changing polymer, and then having two poly-3-hexylthiophene-based solar cells in which to drive that between its colored state and its transmissive state. I think what's nice about this is it shows how you can bring these various types of organic electronic devices together into a flexible module. Now, I'm really going to have to get this slide updated because we're doing a little spraying over here, and please note that that says GT for Georgia Tech. But I do want to work through the chemistry here to finish up. And that is that what's nice about what we're doing is we're making organic soluble polymers, and they are organic processable. We spray a lot from toluene. But we also have the ability to make water-soluble polymers. And if we saponify the ester of this polymer to its dicarboxylate salt, this polymer is water processable, and it can be sprayed to make films. There's a film here on ITO glass. Now, what organic chemists know is that carboxylic acids themselves are relatively water insoluble. And so the polymer here, after acidification, is resistant to both organic solvent and water to dissolution. And so we can switch this polymer electrochromically in an aqueous solution. I believe we're using sodium nitrate in water here as we go between the color state and the transmissive state. And again, you can see, looking at the transmittance changes, that we have good, strong transmittance changes with quarter-second switching. So why might we care about this? And one of the aspects that we all think about is, well, what are the environmental impacts of what we do? And I want to put a little bit of a different spin on environmental issues in terms of these types of electroactive polymers. First, these water-soluble polymers can make large area, thin films, and what I think is important is the environmental impact will be minimal in the processing locations. In essence, where people are going to be putting these together and creating these devices, not having to use organic solvents, either in the processing or in the construction of the device. These materials, then, being very polar, they can be applied to these ITO-coated substrates, and Seth showed very nicely how ITO can be modified with various levels of polarity and work function. And so these flexible substrates then work very well for these water-processable electrochromic polymers. As I said, they are aqueous compatible, and so we're able to switch them in water, and this gives very rapid switching speeds. And then the last thing has to do with this processing aspect. And what I want you to do is to think about the Empire State Building, and what you might not know is that over this last couple of years, all of the windows in the Empire State Building have been replaced with low-E glass. That's over 6,000 windows that have been replaced. That's 187,000 square feet of glass that has been replaced in the Empire State Building. Now, those are not electrochromic windows, unfortunately. Those definitely not my polymer, unfortunately. But if we were to put a 0.5 micron active coating of our MCCP material onto the Empire State Building, it would take 20 to 30 pounds of the polymer, in essence, to coat all 187,000 square feet. And so when we think about chemistry, and it was mentioned earlier how we are looking to scale up the chemistry in laboratories that we're building here at Georgia Tech, you can make an impact in some relatively large projects with small amounts of material. And certainly for our collaborators, BASF, making 20 to 30 pounds of polymers is trivial. And so using chemistries that might involve Suzuki chemistry, Stille chemistry, direct arylation chemistry with palladium, this is okay. Because you're able to make a small amount and apply it to a large project. But where the gain is when those materials are then sent on to the engineering company that's going to be doing the processing, and they don't want to use dichlorobenzene, they don't want to use toluene, they can use alcohols, they can use water, etc. Okay. Where I want to finish up then has to do with, ultimately, we need to think about the stability of these. A collaboration with Sam Graham, and this is a double protected electrochromic device, again, one of our MCCP-Magenta devices that was studied here in a collaboration with Sam's group. And what you can see here are some photographs of the devices and the conditions in which these devices were held for 40 days. And so inside a chamber at 50 degrees C and 80% humidity, you can see that the transmissive state, in essence, held for that 40 days, and there was a little bit of loss of color over that 40 days in the magenta state under those conditions. And so we have really quite nice stability at relatively harsh conditions in these laboratory-built cells. And so we feel that the cells themselves, in terms of moving ahead towards window-type devices, are potentially useful there. The other aspect then has to do with energy. And I'll just focus in on the right-hand side here today to point out that as these polymers are films on electrodes, then they have electrochromic memory. And in essence, what we're doing here is we are setting our polymer either in the absorbing state or the transmitting state. We are giving a 5-second pulse of 2 volts, and then we are sitting at open circuit for 900 seconds. And we are holding that color, and depending on whatever voltage we have, we could set any level of transmission in between here and have that stability. And so very low amounts of energy are required in these electrochromic devices, which means you can use them where they're going to be powered by local power sources like batteries. And I think the last piece of information I want to talk about is this very recent experiment that was done that has to do with the photo-oxidative stability of this ECP-Magenta polymer. And what was done here is these 5 samples were sprayed onto ITO glass or glass, I don't remember right now, and they were placed into containers either in air or, in air on the right-hand side and argon on the left-hand side. And then they were irradiated in a weatherometer for 24 hours. And what you can see is that there's photo-oxidation in air. And the point here, and I'll even knock on the table, is yes, this is exactly what's supposed to happen. We make those polymers easy to oxidize on purpose. So if that didn't happen, I'd actually be concerned. But what's nice is that when we do not have oxygen present, the material is very stable. It's stable to color, it's electrochemically stable, it switches, it's electrochromically stable also. Okay, so I think that is going to be it for today. I will just go ahead and stop, and if there are any questions, we'll go with that.